Last time, we used betting strategy ideas to show that for any submartingale, the number of times it crosses upward over any particular interval is controlled in a nice way by the values that it takes at the beginning and the end of any time interval you wish to consider. That's a very powerful tool because it allows us to control how many oscillations the paths of the martingale have. Let's just think for a few minutes about oscillations of arbitrary sequences. If xn is any sequence in even the extended real line, you can let it take values plus or minus infinity if you want, then again, let's denote by un of x the number of up crossings over the interval from a up to b, the number of times x crosses up from a to b in the interval from time 0 up to time n. We could write that, again, in terms of the stopping times each time it falls below A and each time it rises above B. In this context, where we're not even necessarily talking about a stochastic process, but just a sequence, those are just some times that are determined by the values of the sequence. So just for example, to understand what this statistic means, if our sequence xn is increasing, then the number of upcrossings can't be very big. Indeed, it can never be bigger than 1. It might be 1 because we might start below A and rise above B eventually at some finite time, and then we'll have 1 up crossing, but we can then never drop below A again since we're increasing. On the other hand, it could be 0 if we start above A to start with, or if we never rise above B at the end of the day. If xn is a decreasing sequence, then the number of up crossings for any interval will be 0 because we never cross up at all. So those are two extreme examples, but the thing I want to note is that in both of those cases, we know that our sequence will converge. An increasing or a decreasing sequence will converge in the extended real line. Let's think about what kind of convergence properties sequences that have bounded number of up crossings will have. Suppose that we actually don't converge in the extended real line. That is, suppose our sequence has a lim sup and a lim inf, and they're different numbers in the extended real line. Well, in that case, the lim inf is, of course, strictly less than the lim sup. Now, if I have two extended real numbers that are not equal, one is strictly bigger than the other, then I can find some numbers in between. In fact, I can find an infinite sequence of numbers in between, and in fact, I can find an infinite sequence of rational numbers in between because the rationals are dense. So that means that I'll be able to find two rational numbers that are strictly in between the lim inf and the lim sup. Now, the rationality will be helpful to us in a few minutes, but regardless of that, for any two numbers a and b, if we have this situation here, it then follows that the limit as n goes to infinity of unx of ab, which is a limit that exists in the extended natural numbers because un is an increasing sequence, that must be infinite. Why is that? Well, because this tells us that there is a subsequence of xn that eventually stays below a. And this tells us that there's a subsequence of xn that eventually stays above b. And so that means that we have to repeatedly keep going above b and then later below a, and then above b, and then later below a, and so on. So we must cross upward from a to b infinitely often for this to happen. Now, as I noted, because un is a non-decreasing sequence, it always has such a limit. Let's denote that limit as u infinity. And so what we can learn from that is that if this number here, the limit of these, is not infinite, then the sequence must converge in the extended real line. Well, now we think back to what we proved last time with Doob's upcrossing inequality. That told us that at least in expectation, this number of upcrossings up to time n is controlled by some constant, depending on a and b, times this statistic here, which depends only on the values of the process x at time 0 and time n. So in particular, if we have some kind of uniform in n control on that right-hand side, we'll get that this thing has finite expectation for some particular a and b. If it has finite expectation, then it must almost surely be a finite valued random variable. And if we can therefore do that for all rational numbers a less than b, then we can take intersections of countably many things to show that almost surely un is going to converge. That's what we're going to prove right now, and actually it's even better because this argument would only allow us to conclude that the sequence xn converges in the extended real line, whereas in fact it's going to converge to a real number. That's our theorem, the first version of the Martingale convergence theorem right now. If x is an L1 bounded submartingale, then it has a limit. Xn converges almost surely to some random variable x infinity, and that random variable is real valued. Not only that, but the random variable is actually an L1 random variable. Now, I've actually already outlined more or less the full proof of that for you in the discussion a moment ago. We'll go to the details in a second, but let me just note that we don't even really need to assume explicitly that xn is L1 bounded. That will follow actually from this, what looks like weaker assumption, which is that the positive part of xn has bounded expectation. And that's because if I take the L1 norm of xn and write that therefore as the expected value of the sum of the positive and negative parts of xn, well, I can write that in this funny way. That's the same thing as twice the positive part minus the difference of the positive and negative parts. But the difference of the positive and negative parts is just xn itself. So that's twice the expected value of xn plus minus the expected value of xn. And now we use the fact that x is a submartingale, which means that its expected value is non-decreasing, so the negative of it is non-increasing, and this is less than or equal to the negative of the expected value of x naught, which is fixed for all n. And so that means that if this is bounded as n increases, then this will be as well. So we can restate this by assuming that x is a submartingale whose positive part has bounded expectation. Let's turn to the proof. So for any real numbers a and b, by the Doob upcrossing inequality, we have that the expected value of the number of upcrossings in the time interval from 0 up to n is no bigger than 1 over b minus a times this difference here. And now we can bound that fairly bluntly, actually, by taking the expected value of the absolute value of each of the terms, and that'll give us the expected value of the absolute value of xn plus the expected value of the absolute value of x naught plus 2 times the absolute value of a. Now that's true for any fixed n, but of course under our assumption that's going to be less than or equal to the supremum over all k of the L1 norm of xk plus these other two terms here which don't depend on n. And so that bound is finite. Now the sequence unx of a and b is a non-decreasing sequence, and so we know that it converges to a random variable u infinity, as we noted, which could be infinite in principle. But therefore, by the monotone convergence theorem, we get that the expected value of u infinity is equal to the limit, as n goes to infinity, of the expected value of unx. But we have that that is less than or equal to this quantity here, which is finite. So that shows us that for any two numbers a and b, the expected value of this random variable, the number of upcrossings in total from a up to b over all positive time, is finite. So in particular, that tells us that this random variable almost surely takes finite values. That is, if we fix a and b and let omega a b be the event that ux at that realization omega at infinity of a and b is finite, then that event has probability 1. Now comes the necessity of restricting to rational pairs a and b, so we have a countable family. If we let omega naught be the intersection of all of the omega a b's, where a is less than b and a and b range through the rational numbers, then that is a countable intersection of probability 1 events and therefore has probability 1. Notice that on this probability 1 set, omega naught, x infinity, which is the limit of xn, must exist by the argument that we made at the beginning of this lecture. It must exist as an extended real-valued random variable. And so to conclude the proof, it suffices to show that this limit random variable is actually in L1. If it's in L1, then it will almost surely be finite valued as well. And to finish that proof, we're going to use Fatou's lemma. If I take the L1 norm, which could in principle be infinite, of this limit x infinity, well, that's by definition the expected value of the limit of the absolute value of xn, and that limit is therefore a lim inf. By Fatou's lemma, that's less than or equal to the lim inf of the expected values, but that lim inf is certainly less than or equal to the supremum of those expected values. And that is, by assumption of the problem, finite. So that shows that this is an L1 random variable. And that concludes the proof of this submartingale convergence theorem. Now, before we go on, I want to note one slightly subtle point here. We've shown that we have a sequence of L1 random variables that's actually L1 bounded, and it converges almost surely to an L1 random variable. That does not mean necessarily that xn converges to that limit in L1. Indeed, as we've already shown from the Vitali convergence theorem, this happens if and only if the sequence xn is a uniformly integrable set. Now, we do know one family of martingales that are uniformly integrable, and those are the regular martingales, where xn is given by conditioning some fixed L1 random variable on the sigma field at time n. Well, now we're going to prove the second version of this Martingale convergence theorem, which tells us that that's actually an if and only if. Submartingales that are L1 bounded always converge almost surely to L1 random variables, and that convergence is in L1 if and only if the martingale is actually regular. Now, in that case that it is regular, we can always take this variable that we're conditioning on to be that limit x infinity, as we'll see right now. Now, I'll also note that there is a submartingale version of this. If xn is an L1 bounded submartingale, then it is uniformly integrable if and only if xn is always less than or equal to the conditional expectation of its limit given the information up to time n. I'm not going to take the time to prove that. You can see the proof of the submartingale version, if you'd like, in this corollary in Driver's notes. It's not very different from the proof I'm going to write here. It's just a little more involved using conditional Fatou's lemma. So let's prove the theorem as stated here for martingales, which is the place we will most often need it. For the forward direction, suppose that xn is uniformly integrable. Then by the Vitali convergence theorem, since we know that xn converges to x infinity almost surely, and therefore in probability, it follows that xn converges to x infinity in L1, as we need. Now, because of that, if I fix any n and consider the sequence of m's above n, then by the martingale property, conditioning xm on fn just gives me xn. But this is actually going to converge as m goes to infinity to the conditional expectation of x infinity on fn. Why is that? Because if I take the L1 norm of that conditioning difference, well, the conditional expectation is linear, so inside there, that's the same thing as the conditional expectation given fn of the difference xm minus x infinity. And we know that conditional expectation is an L1 contraction. So that's less than or equal to the L1 norm of xm minus x infinity, which, as we stated above from Vitali, goes to 0 as m goes to infinity. So that tells us that this converges to the conditional expectation of x infinity given fn. But this is constantly equal to xn, and so therefore we get the equality that we sought here. and we see that x actually is a regular martingale given by conditioning x infinity on the information up to time n. For the converse, suppose we know that that's true. Suppose that xn is the conditional expectation of the limit, which is L1, given Fn. Well then, xn is a regular martingale by definition, and from what we proved earlier in lecture 48.1, it follows that xn is a uniformly integrable set, which concludes our proof. Now let's give one more variation on this theme. Let's talk about LP-bounded martingales. If p is strictly greater than 1, and if xn is an LP-bounded martingale, well, first of all, LP bounds imply L1 bounds. That's by Hölder's inequality, actually, as we'll see in this proof. And so this is a special case of what we just considered. We know we're going to have an almost sure limit, and it's going to be a limit in L1 if and only if the sequence xn is uniformly integrable. But we know that any LP-bounded sequence is uniformly integrable, so we'll for sure get L1 convergence. But we'd be more interested in LP convergence here than L1 convergence if we're measuring everything in LP. And we can get that too. Here's the result. If xn is an LP-bounded martingale, then, as before, it has an almost sure limit x infinity, which is finite valued. And in fact, that limit x infinity is LP. Moreover, the convergence is in LP as well. And therefore, it follows that xn is a regular martingale without the explicit assumption of uniform integrability because LP-bounded sequences are uniformly integrable. So let's prove all this. It takes a little bit of piecing together of various tools that we've developed over the last many lectures. Let's let yn denote the absolute value of xn to the pth power. Since xn is a martingale, that means that yn is a submartingale because the function x maps to absolute value of x to the p is a convex function. Now, moreover, if we look at the L1 norm of yn, well, that's just the expected value of the absolute value of yn, which is the expected value of xn absolute value to the pth power. So that's the LP norm of xn to the pth power. And it follows, therefore, from the assumptions that the supremum of the L1 norm of yn is the supremum of the LP norm of xn to the pth power, which is finite. So we have that yn is a non-negative submartingale, which is L1 bounded, and so by the martingale convergence theorem that we've already proved, y infinity, the limit of yn, exists almost surely and is actually an L1 function. We can also note that xn measured in L1 norm, well, we can write that in this funny way. That's xn times 1 in L1 norm. And now we can imply Hölder's inequality with our exponent p. That's going to be less than or equal to the LP norm of xn times the LP prime norm of 1. But the LP prime norm of 1 is just 1, since it's the expected value of 1 to some power. And so that's just the LP norm of xn. This is a very simple inequality which we just haven't noted before. That is, the LP norms in a probability space are increasing as p increases. And so in particular, that tells us that LP is contained in L1, which is something we did already note. Now, for our purposes here, what that means is that we can conclude that xn, the original martingale, is itself L1 bounded because xn is LP bounded. Thus, xn is an L1 bounded martingale, and so it also has a limit x infinity, almost surely, which is an L1 random variable if we want. But of course, we can now compare these two because they're clearly closely related. If I take y infinity, that's the limit as n goes to infinity of yn, but yn is xn to the p, and that limit is just x infinity to the p. Now y infinity is in L1, and so that means that the pth power of x infinity is in L1, which is to say that x infinity is in LP. So we've shown most of what we stated above. We do have an almost sure limit, which is in LP, and we can conclude that xn is a regular martingale just from the fact that it's uniformly integrable by the fact that it's LP bounded for some p bigger than 1. So the only thing left to prove is that we actually have LP convergence here. Now we have to go back to the Vitali convergence theorem. We proved that theorem in the L1 case, but if you look carefully at our proof, you'll see that it works exactly the same way to show LP convergence following from convergence in probability, provided we have this condition. We need to have the pth powers of the terms in our sequence be uniformly integrable. So that's what we need to show here, that the sequence yn is uniformly integrable. Well, to show that, we will employ the very first example of uniformly integrable random variables from that lecture, 48.1, which is if our random variables have a uniform dominating function that is integrable, then they are uniformly integrable. So we're going to find a uniform dominating L1 function for the sequence yn of pth powers of our original martingale sequence. And here is that L1 variable. It's just going to be the supremum over all m of xm to the p. We'll call that g. Now, this inequality is, of course, obvious, but what isn't so obvious is that this is L1. In fact, this could be uniformly equal to infinity, for all we know. So we need to show that this is actually an L1 function in order to conclude the result here. And here is where the Doob LP martingale inequality will come in handy. The expected value of g, this non-negative function, is the expected value of the supremum over all m of xm to the p. Well, that supremum inside there is the limit as n goes to infinity of the supremum over m less than or equal to n of xm to the p. And now by the monotone convergence theorem, we can pull that limit outside, since this is an increasing sequence here. If I increase n, I only increase that supremum. And now we employ Doob's martingale inequality, which exactly says that this expected value here is bounded above by a constant, that's p prime to the p, times the expected value of just xn to the p at the endpoint. So that shows that the expected value of g is less than or equal to the lim sup, as n goes to infinity, of, well, p prime to the p times this expected value of xn to the p. But that lim sup is certainly less than or equal to the supremum of these, which we assume to be finite in the statement of the problem. Alternatively, this lim sup is actually equal to a limit, because we already showed that xn has a limit x infinity, which is in LP. So if you like, we could even write this as p prime to the p times the LP norm of x infinity to the pth power, which is finite. So that shows that yn has a uniform dominating L1 function. This expected value is finite, which means that it's uniformly integrable, which means that by the Vitali convergence theorem, xn converges to x infinity in LP norm. And then finally, as we already noted, the LP boundedness of the sequence xn automatically implies that it's uniformly integrable, which means from the last version of the Martingale convergence theorem we proved a few slides ago that xn is regular, concluding the proof. Now there's other versions that we could talk about. We could talk about supermartingales. We could talk about what happens if the process is not L1 bounded. How bad can it be? It turns out that we either will get convergence or we'll get wild oscillations. We can't have anything in between. But we're going to satisfy ourselves for the discrete world of martingales with these results that we've already proved. We'll just make one final note here using these results to prove another version of the optional sampling theorem now. Remember, the optional sampling theorem that we proved required the stopping times that we used to be bounded, and we saw examples where that assumption can't be removed. Well, it turns out that if we're in the world of regular martingales, that assumption is not required. And so, to conclude this section of the course on discrete time martingales, we have the optional sampling theorem part 2. If xn is a regular martingale, like the kinds that we've seen arising from the conclusions of the previous Martingale convergence theorems, for example, and if we denote by x infinity the limit that we know exists. Then for any two stopping times, sigma and tau, first of all, x tau is given by conditioning x infinity on f at time tau. The L1 norm of x tau is finite and in fact bounded by the L1 norm of x at time infinity. And best of all, if we condition x tau on f sigma, we get x at time, whichever one is smaller, tau or sigma, regardless of whether tau or sigma are bounded or not. And to be clear, this formula makes sense even if tau and sigma take infinite values, because x infinity now always makes sense. The proof is a very straightforward consequence of all of the results we've now proved. First of all, since by assumption xn is regular, we've shown that it is uniformly integrable, and therefore by the Martingale convergence theorem that we proved a few slides ago, xn can be computed by conditioning x infinity on fn, but that means that this follows essentially by definition, as we showed in lecture 45.3, how to condition on the sigma field f tau. Now from there, we get that the absolute value of x tau is equal to the absolute value of conditioning x infinity on f tau, but by the properties of conditional expectation, that's less than or equal to the conditional expectation of the absolute value of x infinity. And now if I take expected values of both sides and use double conditioning, that's equal to the expected value of the absolute value of x infinity, which is its L1 norm, which is finite, which gives us this statement here. And finally, for the typical statement here of the optional sampling theorem, we just have to use the general Tower property that we proved in lecture 45.3. If I condition x tau on f sigma, well, because we get x tau by conditioning x infinity on f tau, that's given, as you showed on your homework, by conditioning x infinity on the sigma field at time sigma min tau. But that is, by the result here, equal to x sigma min tau, which concludes our proof of this version of the optional sampling theorem. And as usual, the principal application of this will be to take sigma equal to 0, and note that by taking expectations, the expected value of x tau will be constantly equal to the expected value of x0, even for an unbounded and possibly infinite stopping time, in the case where the martingale in question is regular. That concludes our discussion in this course of discrete time martingales, and we will now move to the last part of this course, continuous time stochastic processes and their regularity properties.